This is a community garden here at UCSD, and we're also kind of a lab for students on campus to do their projects.
Aquaponics is a eons-old system of growing fish symbiotically with plants. Somewhere around the dawn of agriculture, when farmers realized that adding carps to their rice fields not only reduced the number of pests, but simultaneously increase the yield as well. Here we plan to bring that sort of technology into the 21st century just like anything else. And we are going to introduce a whole bunch of different computer sensors into it. Each sensor is going to be assigned an IP address or a USB serial address, and they will all communicate with a centralized computer node. However, later we plan to actually have a two-way interchange between our data and our system. So right now we're only getting it coming to us, but we would like to be able to automatically have our system play with that data and, let's say, send more water downhill. So if it's low in potassium, we add more potassium.
This is our Aeroponics project. It is a technique of farming and gardening popularized by NASA. It's revolutionary in the fact that it does not require any growing media whatsoever. In order to compensate for the lack of growing media, what we do is we atomize water. We pass it through a pump that pumps it around 40 psi. Then we pressurize it in the accumulator tank. That accumulator tank brings it to the Goldilocks zone around 80 to 100 psi. We have a simple solenoid, which is basically an electrical valve that regulates when to release the 80 psi to 100 psi water. That travels through these high pressure tubing. The tubing then enters these totes. Once the atomized water exits the misters, it directly hits the plant roots. The timing of the mister is typically around 8 to 10 seconds. So we do that every like 5 minutes, depending upon the type of plant. And then that constant spraying and misting of the plant would result in extreme nutrient input.
I've been working on the anaerobic digester project here for a little bit over a year. Basically, there will be bacteria that will digest this food and break it down to generate biogas as well as sludge. And the biogas can be used to generate electricity, while the sludge can be used as like a nutrient-rich fertilizer. Been processing about 300 pounds of food waste per week. And a lot of it comes in like really big chunks. So first we have to go through a pre-processing system, garbage disposal, as well as a sewage pump that will pump it into this first tank. This first tank, the hydrolysis tanks, that'll move over to the second tank here, and the third tank, which are both methanogenic tanks. So basically there's like methanogenic bacteria in these that will break down like the smaller polymers and convert it into methane. Piping here that goes into a bag here to store like the dirty unpurified gas. And then we're going to be putting that through like a water scrubber here, which will act as like a carbon dioxide filter. And then from there, we'll have like a hydrogen sulfide filter and a water trap. And then that'll be going into the second bag right behind here.
Another output of the system is all the digester that comes out. Once it comes out from this black container that you see over here, we immediately aerate it using this air tube to begin killing and destroying all the anaerobic bacteria. It filters all of the big chunks and solids into these two containers, and then once the remaining digest is just in a liquefied state, it gets pumped into a nitrate processing chamber that also contains a lot of these filters in finite, really small mesh pieces that houses and grows nitrifying bacteria. The oxygen dissolves in the nitrate bacteria to allow for all the ammonia to convert into nitrates. Once we get enough biogas and it's converted into electricity, we convert it all to make it a self-sustaining system. Contained here is going to be used for hydroponics, which produces plants that can also be put into the digester and make a self-sustaining cycle.
Starting from Jose water treatment project, once the nitrate-rich water is ready, the water is gravity fed to the reservoir where the pH and the nutrient content is adjusted. The water will pump up through this line to the top of the biogas system, where the nutrients firm technique trays will be set. After passing the NFT system, the water will come through this pipe and return back. This will cause a constant movement of water, enabling enough dissolved oxygen for the growth system. In the future, we intended to use this area between the NFT trays as a living wall. So imagine a green wall, no, a green roof.
So what we're going to do is with the biogas system, we're going to have the biogas hooked up to a generator, which then connects to our batteries. When our solar batteries drop beneath a certain point, like let's say 10%, the biogas generator will kick in and act as a backup power supply. We don't have any one, large group and everything. It's all, we still have the silos, but those silos are all communicating with each other. We have the waste transportation, we have the waste processing, we have the gas purifying, we have the wastewater treatment, and then we have the hydroponics, and then we have the renewable energy grid that ties it all together. So that's 5 different student organizations, 5 different student projects, all going on and all working with one another, because that's really the only way you're going to be able to build projects to this sort of scale. Because the raw reality is you have about 4 years as top of all the classes that you need to do to make something happen, and no one person is ever going to be able to make this possible.
We're all different majors. I'm a biochem major. You're a computer engineer. Enid's environmental chemistry. We have biology. We have art major. We have everything here, and everyone works together because we all have kind of the same interest in gardening and